Welcome to Grayscott Thursday. Grayscott Thursday is a series of webinars we organize every Thursday at 10 on various HPC topics, such as this one today about Eve, which will be presented by Joël Falcou, who will be introduced later on. But first, let me give you a little presentation of the organization team. So there is Pierre Robert, a research engineer from the lab, a French laboratory of physics and particles in Annecy, in the French mountains, and Karim Azoum and I from TerraTech, and within the French NCC called CCFR, and with the lab of Annecy, we co-organize the Grayscott Thursdays and the Grayscott School. Because those 17 Grayscott Thursdays that you will discover are held by 9 incredible teachers who will each one of them give you webinars on their topics, introducing at the same time the program of the summer school. So what is Grayscott School? Grayscott School is a free summer school dedicated on programming and optimization on heterogeneous architectures. It was created 2 years ago by Pierre with a few people in Annecy, and we, the French NCC, joined him last year to help him develop it not only in Annecy, but also in 12 satellite sites among 4 countries. So those satellite sites helped us reach more people by broadcasting the school live in their locations. The summer school had a 2-week program, 1 week on CPU and 1 on GPU, but everybody was free to choose the courses they wanted to attend thanks to our à la carte option. So we finally trained over 500 people, and everything is available still on replays on our website and YouTube channel. You can access it if you want, but I must warn you that everything is in French. This year, we are going European, so all will be in English, like this webinar. So you have various ways to attend the school, as you'll see in the video I'm going to launch for you. And also we invite you to be part of the team and become a satellite site yourself if you want to host the school at your place. We are able to provide you everything, all courses, containers, access to the teachers, and also we can connect you with our growing HPC community. So please let me now play the video for you.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grayscott School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or a la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Cycle, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, CuPy, CUNumeric, JAX libraries, and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G Fortran, and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Nsight, Malt, and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together, and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
If you have any question regarding the school or anything, you can ask them in the Q&A section, and Pierre and I will be glad to answer you, with Karim, of course. Now, thank you for listening to me. Now I'll give the floor to Pierre Robert himself, the creator of the school. Pierre, maybe you can introduce Joël?
Yes, thank you, Mary. So, of course, Joël is a part of the Dream Team, as you may guess. And so Joël is involved in Code Recon for teaching and to make sure that people learn really good stuff about programming, about software engineering, generally about C++ and modern C++, so C++ 20 as we will discuss today, with a lot of tricks and a lot of things to do. You will discover a new language, basically, if you didn't program in C++ 17 or 14 or even 11, you will see that C++ 20 is really, really powerful. He's also involved in the LRNS laboratory, so for research also. So you are involved also in several PhDs. You deal with several PhD students and with a lot of research. So with Eve, for example, that we will discuss today, also Kiwaku, that we will discuss also maybe one word today and maybe a bit more during the school. Also a lot of scores. So there is a full universe of project around this new feature in C++ 20. So I will give the floor to Joël. He will explain that really much better than me. So Joël, it's yours.
Thank you, Pierre. So let's get started and speak about Eve. And for that, I'm going to drop a bit of a context to understand what we are going to speak about. Okay, but basically, Eve is a C++ 20 library that lets you access and design algorithms using the SMD instruction set inside your CPU. So this is a CPU-centric presentation. So I don't know if you already went to all the GPU ones, but it will be slightly different, but yet slightly a bit the same. So this is a collective work. I will say it again, but I want to emphasize that this is a project where a bunch of people are involved, the main contributor being myself, Denis Jaroszewski, Jean-Thierry Lapresté, and most recently Alexis Owen, which are all working on different parts of the project. But we are going to dive into this a bit later. So what are we going to speak about? So why should we care about SIMD programming? And even better than that, what is SIMD programming? So you may have been used to program on a single CPU with regular instructions. Okay, you got arithmetic and logical unit. You feed it instruction, you feed it data. The LU do its things, and you get some results. It's obviously more complicated than that. You have all the issue about out of order instruction scheduling, micro instruction repurposing, you got branch prediction, you got a lot of things. Okay. But in the end, this classical single instruction, single data process is what you get most of the time if you don't ask for more. Okay. Obviously, one thing we can do is to say, what if I actually process more data per instructions, okay, which give us a classical thing, which is a single instruction, multiple data systems, where in this process, you end up with registers that are larger than usual, from 128 up to 512 if we are realistic, and more than that if you like to play with fire, up to 2014 bits on some system. And the idea is that in those 128 or in these 256 bits, well, I can shove more data. Okay, so if I take, for example, a single precision floating point value, right? It fits into a single 32 bits register, right? And if your register is suddenly 128 bits, you get 4 of those floats in a single register. And the SIMD units are made so that when you process those wide registers, let's call them like this, you process them roughly at the same latency that at the other instructions, except you computed your operation on 4, 8, 16 value at a time, which means that we expect a speed up of about, well, the size, the width of the register, the number of what we call the lanes of these SIMD registers. And so the idea is, well, sounds like low-level things to do. So probably this is something the compiler is doing for us. Sometimes it does. We are going to see how and when. But as soon as the code becomes more complicated, or you start using functions that are not that easily available at this level of granularity, the compiler will just throw the towel and say, okay, you know what? Here's the sequential code. It works. Be happy with that. And we are going to see later what we can do, but I'm done. So you may want to dig into trying to force, your code to go onto this kind of system. And this may require a bit more, work. How many of these systems actually support those kind of instruction set? And contrary to what we could believe, okay, there is a lot of systems supporting such instruction sets. Started back in the late 90s, 1998, and something like this, with the x86 SSE2, which is probably the most known of those systems. But on x86, it quickly evolved into a myriad of subgenre, okay, all the SSE variant, in 128 bits, then in the early 2000s, the 256 bits with AVX and whatever, and a bit later, 2010, 12, 15, I would say, the 512 bits variant, okay, with AVX 512. There is more to come, but that's basically what you have right now. On the other side of the architectural landscape, ARM and PowerPC also supports various instruction sets. Neon is probably the most well-known for ARM. Nowadays, if you are dealing with large server, you may have heard about SVE or even SVE2. And PowerPC, which is a bit on the side, alas, have a very strong support for something called Altivec on all flavor of PowerPC since Power 7. They doubled into the 256-bit with the bridging queue that is now a bit on the side too. And there is also newcomers like RISC-V, which is very much similar to what SV does. And something I consider a CMD platform like Wasm, which is actually a web-enabled assembly support for a lot of things that also supports vectorization. So the actual issue is not that we don't have the tools to go there. We have pretty much too much of them. Because the joke, obviously, is that if you want to write a piece of code doing whatever, you basically have to choose for what you are writing your CMD code. Okay, is it because I'm targeting some x86? Okay, which one? Okay, so maybe I should stick with SSE2, which is what most of the compiler does because it's safe, it's old, everybody has that. Or maybe you want to go faster and you want to target AVX, but that means that any CPU before 2008 is not supported. AVX512 is another piece of issues. ARM is a bit more stable, same for power, but in the worst case, if you want to go on x86 and ARM, which is something that you may want to do at some point, that's two different instruction sets to use. And obviously, because if not, it won't be funny, they are all different. They are all their own, syntax quirks. They are all their own subset of functions they support, their own subset of types they support. And obviously, you cannot just write some code and go somewhere else and be happy with that. So it's a huge commitment in terms of what your code base is going to look like if you want to go and use those instruction sets directly. And what kind of commitment are we speaking about? We are going to see that a bit later. But yeah, why should I be interested into that? Sometimes you can't use GPUs, and the vectorization process gives us sort of a GPU look and feel because you are dealing with those large resistors that you can. It's basically, I mean, you can say that. A GPU warp is probably akin to a CMD register, and then if you have a multi-core of those, we are going to find similarities. But sometimes you cannot use a GPU because consume too much energy. It's not practical for your actual application / systems because maybe you are dealing with an actual physical system that you cannot put a GPU inside physically. So you may want to have something else. And multi-cores is maybe not enough. So you want to go there, fetch this time 4 times 8 speed up on top of whatever your multi-core system is giving you to get there. As I say, you can use autovectorization. You can use some special compilers or some pragmas, OpenMP as a SCMD pragma, which I think is just a way to tell the compiler that you are sure it can autovectorize something. Okay. You can use some libraries, either standard or not. So there is this std unsec execution policy that you can shove to force the compiler to vectorize your code somehow. It's working for some cases, but not for all. Okay. You've got HPX, which is also something that try to emulate that. You can use specialized tools, which are libraries that do something very precise. So ALID is an image processing tool. SIMD JSON, I mean, it's all in the name. It's a SIMD-enabled JSON parsing library. But if your use case is not already optimized by someone, you are going to write that by hand. And yeah, it's not very funny. How much non-funny it is? Well, let's just write, I don't know, a times b plus c using integers, okay? So you can do it in SSE4. We have add and mul over a register of integers. So this is whatever the code is. So we have this special type, okay? This 108 register, which is basically, as it says, it's a 128-bit register of integers, okay? And we have this lovely looking function like intrinsics. So basically, this is an addition and this is a multiplication of the low part, okay? Because the high parts will give you a 64-bit result, but you don't want that. So you can do that. On Altivec, it looks completely different because the only way you have to do this multiply addition is going through floating point. So you may want to convert, do the multiplication, convert back to integers. And you can try write that in SSE2. And as I said, good luck, because it doesn't fit into a slide. You have no way to do this. There is no multiplication operation on 32 bits in SSE2. So you have to write it by hand by, slicing it into 16 bits, doing all the, like you do in school, you do the part-time multiplication and then the sum and whatever. It's ugly. And you're not even sure this is the best way to do it. ARM look like a bit like Altivec in the sense that you got a lot of function directly. So that means that you have to basically learn 3 new or 4 new intrinsic set types, idioms, and it's not going to scale if you want to keep that into something manageable in terms of code base, right? So you don't want to do this, and if you do, you want to isolate this piece of code as much as you can from your actual business / simulation code, because it will just turn the algorithm into a mess. And so yeah, that's why we wanted to do something about it. Okay, Eve is a very old project, started a long time ago, like 2005, 6, something like that. So it evolved through 2 decades of architectures, 4 different C++ standards, and the current version is a C++20 library. And basically what we do is that we wrap all these things, okay, into something that is manageable to use in a regular piece of code. Okay, so we have a library of core types that will wrap those intrinsics and wrap those types, so we can actually make sense out of them. Okay, we have a lot of numerical function, basic one, maths, and so on. And we also have support for large-scale algorithm, stuff like the STD algorithm, but we guarantee to be vectorized. We support all x86, ARM, PowerPC things quite well. We have an extensive set of tests. We have work in progress, more our work and more our progress on RISC-V and WASM. We know it works. It's more like we need to fill in the blank for RISC-V, and we need to make sure it works properly in WASM. It's both licensed, so you can download it, use it, and we don't care about what you do with it. Send us an email or a postcard. I'd like to know who is using Eve. And as I said, it's a team effort. I really much like emphasis on this. We won't be able to do what we do right now without the math skill from Jean-Thierry and the design skill from Dennis and the very, very good help, technical help by Alexis. So you can find us on GitHub. You can play with it on Compiler Explorer, even if it's sometimes flaky. And we also have documentation. Whenever I'm going to send those slides, you can click on that and get there. But if you want to get GitHub, this is the our GitHub, okay? So you can clone and whatever. Basically, the place where stuff are going. And the documentation is there. We have a bunch of tutorials you can play with. We try to have an extensive documentation. Let's take a look so we see what we are speaking about. I don't know, whatever, this one. Yeah, okay, so we try to have stuff with example and whatnot. So yeah, we try to have something of decent quality for these elements. Oh, and we even have runtime examples. So yeah, so we have a bunch of things going on. So you are pretty much welcome to have a look and try to see how it works. So yeah, what can I do with that? Because okay, I know that vectorization is complicated. We have a tool for doing this. What can we do? Well, let's take a short example of something that everyone can understand because the operation is simple. And let's just have a look at what we write, and then we are going to have a look at the generated code. So this is a very bird's view thing. We are going to delve into the detail later, okay? But that's basically what we are right now. So what we are looking at is a vectorized Sterlen function. So I take a piece of strings in my pointer to unsigned char there, and I will just try to compute the length of the string. So what it is I'm basically looking for a 0, and I need to know how many characters I processed. So this is something which is already vectorized if your libc is written correctly, which I assume it is. But the deal is to see that we can actually write it in a slide, okay? And we are going to look at what the result is. And the important thing to see there is that this code, as it is, it's written once. And I can compile it on x86, and I will get whatever x86 flavor you want. I can compile it on ARM. I can compile it on Power, and every time we are going to generate a vectorized code without us having to think about it at the code level. Okay, everything will be chosen by a compilation flags, and we are going to get what we ask for. So how does it work? Well, basically, we take the pointers, we compute some, we do some shenanigans on the addresses, so we know we can start by loading a vector somewhere. We do this load thing, okay, that we're gonna load this data from this pointer and put it into this type, this wide of uint8. So a wide of t is basically a SIMD register filled with value of type t. So this is a register, a SIMD register of 8 bits sharp. So that means that on SSE2, this is 16 char is 32 on AVX, 64 on AVX512. So I'm loading this big block of data. I'm compiling a mask called ignore, where I'm going to speak about that later. This mask is going to help us to get rid of the garbage, because we load data from a place where maybe there is garbage, so we want to clean it up. And I'm trying to find a place where, okay, is there a 0 in this value? Okay, so I can compare my register with this thing, which is a register full of 0. And if there is somewhere a 0, I will get the true, okay? So I'm trying to get the index of the first true value. And this first true function returns me an optional, okay? So it says the location, the position inside the register where the 0 is, or it's nulloped, which means that I didn't find any true in this register. And as long as I don't find any zeros, I'm going to walk 16 bytes by 16 bytes, loading, checking the position of the first true until I get a hit. And when I get a hit, I know that, well, I'm somewhere in my data. Okay, this is the pointer where I am. I'm going to subtract the beginning of my string, so that gives me the position in the number of register where something is happening, and I just have to add the small offset to the local position of my 0, and I get my star length. Okay, so a bit of thing is going on, okay, but it's basically 12 lines, and the cool thing is, here it is, okay, I can compile it, and well, this is the SSE2 generated code. And what we do have is a very tight loop there, where I do my load, I do my comparison, I skip 16, I do my masking, and I check if there is something to fetch for, and if not, I'm keeping there. I can do it in AVX2. I get another piece of register, and this time I'm skipping 32 bytes, every time. So larger register, and then I mask and I do the exact same thing. And I can do it in AVX512. Okay. This time 64 bytes per 64 bytes. And we have a different subset of instruction because masks are different, but we don't care. And I just get my results. So this is a single code with what I would call the somehow high level of abstractions that get compiled into 3 different architectures targets. And that's exactly what we are going to do. We want with Eve to provide this level of control over whatever is vectorized in your code, right? So let's dig into this. So Eve is a SIMD wrapper. We just saw it working. It works by having those typed SIMD wrappers, this wide type, okay, which is defined by an element type and an optional number of lengths, okay. So you can have a wide of int filled with 4. You can have a wide of float. You can fill it using a formula passed as a callable object. So this is 1, half, a third, and so on. You can, as we see, we can load from some piece of memory. All of that are very portable because we don't specify the number of lengths and everything is picked up by the compiler. And you can also, but it's less portable, choose your number of lengths. And as soon as you have something on inside the wide, you can call function on them and they will have the same semantics as the scalar version of those functions, except the operation will be done on every length of the registers, right? So what do we have? We have basic operation, all the operators like plus, minus, divisions, bitwise operation. We got basic math like absolute value, stuff like that. We have a fully vectorized CMAT. So that means exponential, log, trigonometrics, inverse trigonometrics, hyperbolics, and whatnot. Okay. Some of the new combinatorial function like LCM and GCD, stuff like this. We have a fully vectorized set of special functions, Bessel functions, and other math stuff that Jean-Thierry is probably better suited than me to explain. But you put value inside, and there is a funny function with a very nice, LaTeX formulas that get applied to them. We have a bunch of polynomial evaluation scheme, and we have intra-register operation, because this is something you need to do when you want to be efficient sometimes. Everything in Eve are callable objects, so they are not actual functions, but they are objects. Because, as we are going to see, we have support for masking on them or for local semantic changes. The other reason they are callable objects, we are going to see that, is that it helps us write internally a code that makes the discovery and generation of the best code for given architectures easier to do. Okay. So what can we do? Well, we can write code like this. So we have a bunch of wide of int, a bunch of floats also. So you can do this. So this is C+4, which is basically C+4 in every lane. We have an automatic broadcast semantic. You can also mask your operation. So it doesn't work on operator for obvious reasons, but we have function version of those. So add brackets a less than b C4 basically means you are going to compute C+4 in every lane where a is indeed smaller than b. And when it's false, the first parameter is returned. So you either end up with C+4 or with C, depending on where the lane are. So we can do multiplication. You can mask also with what we call relative conditionals, which are conditional based on the size of the lanes. So there we are doing a multiplication, but we ignore the first two. Okay, the first two elements of the register. You can put whatever you want there. This is a constant, but it can be computed, obviously. And then, as I said, we can change the semantic of functions. So I can call exponential like this. We see that we could call add, but I may want to do a saturated add. So instead of having a null u function called saturated add or add s or whatever, we have those small markup that we can put on top of our function. So this is add, and we use the saturated semantic. Okay. So if b plus c is greater than whatever int can represent, we get the max int value, and same on the other way in the negative. We also can use these semantic changes to finally control the precision speed trade-off of our algorithm. When you write SIMD code, you may want to have something that go really fast, but the result will be whatever they are. Or you wish you could vectorize and have the exact results, but it's slower. So in Eve, what we do is that the common function version is in the middle, okay? Or if it can be fast, it's fast, okay? And you can ask for extra precision, for example, using the pedantic marker, which says, okay, now I want you to handle the special case of the normals, infinites, and stuff like this. and I want you to be as close as possible to the standard returns. You can ask for what we call a numeric run, which basically says that you don't take care about nans. So if you compute the numeric minimum, you are going to compute the minimum between x and y, and if there is a nan somewhere, you return the non-nan values. And if you want to go fast, some function supports the row modifier that basically says, I'm doing SIMD for performance. I have no use of those pesky precision bits. So give me the fastest you have for this function. So for example, on SQRT, you will get the raw call to the intrinsics, which is like 12 bits or 14 bits of precision instead of the full-blown one. And obviously, as you see, these bracket operators, it can be combined. So you can say that you want the fast square root, but you don't want to do it on the first value. And you can change those markers as much as you want, and we take care of all the meaningful combination. Another important pattern that we support is swizzle. If we dealing with SIMD register, we can look at them as small arrays of 4, 8, or 16 values. And one classic idioms of vectorization is when you want to shuffle around those values. It's useful because, for example, you may want to do a computation that in scalar has a very complex memory access pattern, but you can look at it as a regular loading pattern, so contiguous values, that you shuffle again afterwards before doing the computation. And this is usually faster. And so we have this shuffle function that you can pass a pattern, okay, with a direct remapping of the index. It's not very portable again because you have the size inside, but sometimes it's enough. You can pass a const per lambda describing the permutation function you want to apply. So this is the same one. This is a reverse. Or for some of them, we actually have a named function that do exactly what you want. So why do we have that? Well, you may end up wanting to compute a non-trivial swizzle parametric function. And what we do is we match your end-written pattern or your end-written pattern function, okay, and we try to see if it's not an actual optimized swizzle we know about. And so all this code do the same thing, because this one and this one will be matched upon to the fact that it's reverse actually. Okay, so you don't even have to know those, because if you unexpectedly reinvent them by passing a function or a pattern, we are going to know that you want to do this. You can also shuffle less or more data than whatever you are shuffling. So maybe if you have a 4-element register, you can shuffle into an 8-element register by, for example, duplicating every one or whatever. Okay. So this is a very important use of SIMD idioms. It's based on various tricks depending on the architectures, and we just abstract them all. I'm going to go fast on that, but basically the way this is implemented is to use make heavy use of concepts and if context per. So we can detect a compile time for which architecture you are currently compiling, and we are going to jump into the most appropriate version of this operation. And inside a given function, okay, we are going to categorize the type you are currently working with to get to the proper intrinsic. This is done so that we can cover all the cases of what kind of type size combo can be optimized on a given architectures, which one need to be emulated, okay, because sometimes some instruction set doesn't support a given type / operation combo. And this starts by having this ABI of constable function that basically take your information. I have this much lane of this type, okay, and by looking at what's going on, I'm trying to know which kind of system you are compiling for, okay? So I'm looking at the size, and so if you are on an x86 machine and your size of your register is 32 bytes, you need to use a 256-bit x86 backend. If you are on ARM and something else happens, we have another marker like that. So we can categorize at compile time for which machine you are currently compiling for. And if you look at, for example, add, we use concepts to specify the ABI, okay, so the actual target. So this is add for x86 and only x86. Inside that, we take your types and we try to know which kind of type it is. So this categorized context for function give us an enumeration that we just say, okay, what are the base type, what is the size in terms of natural lane number, and for each cases, we know what to do. We either call a specific intrinsics, or we need to be sure that we are on some specific variant of x86 to get there. And if not, we can call another function, another add function that will be overloaded for, we don't know which CPU we have, and so we just emulate things. But every time we call a function, we are sure that we have support for it, whatever the type, whatever the lane, and we either emulate it, or we have an intrinsic, or more interestingly, if you have larger than usual wides, we can just unroll it for you. And all of that is completely automatic on our side. So, okay, so what can we do with that? Because I can play around, okay, with a bunch of values and functions, okay, right? But maybe I want to do something more. We spoke about algorithms, and what kind of things can I do with this? Well, we have a full support for most of the STD algorithms. We have a system of views, like the range things. All our algorithms are range-based, by the way, so we get more information about that. And we have a support for container of structs. Wide support tuple-like entities. And so you can have a wide of, I don't know, a wide of pixels, which is a triplet of integers. You can have a wide of a tuple with a 3D position and a mass or something like that. We are going to have an example about that. So it lets us basically play around with this notion of wide by expanding them to other types. So let's have a look at the algorithm first. This is the performance for findIf, for example. So findIf is interesting because it's not just find the value, which is very easy to do. FindIf requires you to pass a predicate. So we support autovectorization of our predicates in our algorithms. So I don't know which one. I think we are finding 0 anyway, but with the predicates. So the blue line is what stdefine does, depending on the type of value we are looking at. This is a 1000 byte data set that we interpret as either 1000 bytes, 500 shorts, or 200 something integers. Why are we doing this? Because when you deal with SIMD, you don't care about the types. Everything just fits into this large register. So the only metric that is important is the number of bytes you are processing. Okay. So it's a bit different than usual benchmark. And basically what we see there is that we basically got, how much is that? 20 something, 8 something, and 10 something, and 4, 5 something. So we get a decent speed up. And this is with every optimization on the compiler set up. So stdefine could actually be vectorized if it could be. And spoiler, it is not. Okay. We can do that with other non-trivial operation, because findIf, if you think about it, you know how to vectorize that. You are just going to do what we did with Sterlen, but instead of looking for a 0, you are going to look for something that verifies the predicates, and you can just chop the find up to the point you find whatever you need. Okay. The only difference we have between this and Sterlen is that findIf is easily enrolled for performance reasons. But there is also algorithms in the STD library, and one of it is removeIf. So removeIf takes a predicate, okay, and it removes the value that fits the predicates by sending them, elsewhere in the container. So it doesn't reallocate; it just moves the data, and all the other ones are at the back. So this sounds like something you cannot vectorize because you are going to move small pieces again and again and again. So if you load a wide, you don't know how many of these are going to move around. Okay, but in fact it is. There is some operation we can use to do that properly, and so we do. Okay? And so we have this classical symmetric, shape of this benchmark. So we are removing 0. And the axis there is the percentage of 0 we found. So if everything is non-zero, it goes very fast because we can just, move everything to the back. If everything is 0, everything stays in place. And for the scalar version of the algorithm, the worst case scenario is 50%, because 1 every 2 elements are going to be moved. It will put a high pressure on your branch predictor. Nobody will be happy. In the case of the vectorized version, as everything is done systematically without branches, as we see, the time are flats. Okay, and we can have a speed up for a char of up to 25 in the worst case scenario. Okay. And in the good case scenario, we still have a speed up of about 4 to 5 for chars and other types. So we have this massive impact even on irregular piece of code like this, which is also very interesting because it helps you accelerate pieces of code that are non-trivial to do so. But the cool thing is you can actually implement your own algorithm with that. So let's do a bit of, as I say, high school physics. Okay, I have a ball that I let drop from some 8. Okay, so as everybody, it's subject to the gravity pulling it down. At some point, it will hit the ground and it will try to bounce up with some elasticity, right? And it will bounce again up to the point I would consider it's basically stationary on the ground, okay, because I can't measure whatever is going on. So this is exactly what happens there. So we have this light ball thing that basically says that B, it's either a ball, which is a struct. We are going to look at the example in details, or a wide of struct. So it's vectorized or not, we don't know. We got our time step, we got our gravitational constant. So first thing I do is I duplicate my ball into the falling state and the bounced state. I update the position of the falling ball by doing some, crude physics. So if there is any mechanician in the audience, I apologize for this very bad approximation of a movement equation. So basically, I'm adding the speed times the time step. Okay, I should probably do something else, but this is enough for us. I am updating the velocity by applying the gravity. Okay, again, and I also compute the speed of the bounced value of the bounce ball by inverting it and multiplying it by the elasticity of the ball. Why do I do the two computation instead of just having an if? Because if needs to be vectorized, and in a way which is a lot like on GPU, you cannot have branches in SIMD. You need to compute everything and then you select. So that's exactly what we do. So what we say is that if my new position is less than some very small amount, I consider that I bounced. So I will return the bounce value, which is basically the same position but upward speed. Okay. And if not, I'm keep falling. And this if else will be applied on all the lanes of the wides. Okay. So for every balls, we are going to test, is it bounce or not? And if yes, should I keep bouncing, keep falling, and whatever? Okay. So if I look at this, let's have a look at the YOL thing. Okay. So we got this ball struct that we register through Eve to tell Eve how it is supposed to decompose the struct. Okay. So a ball is basically 3 floats. The position, the speed, the elasticity. It's a one-dimensional fall. And an integer, which is the number of bounds the ball did. Okay. We have a bunch of convenient functions to extract the meaningful data from the ball structures. Okay. We got our update function that we just look at. So doing exactly what we did. So only stuff I add is I increment number of bounds each time. And then I have a simulation. Yeah. My simulation takes what? It takes these things, a SOA vector of ball. So as soon as you have a Eve adapted struct, you can put it into Eve SOA vector. So what are we doing? We got this vector of balls. I do a transform by applying the behavior on everybody. So this is a transform in place. This is not a standard algorithm. It's just an optimization of when you are computing in place. Okay. So I'm just computing in place my behavior updates. Like the function, I can decorate algorithm. And so this time I ask for the algorithm to use an unroll of factor 2. And then what I do, I use the erase remove if idiom, which is a classical C++ idiom, to remove all the balls that bounce enough by shoving it at the end. Remove if returns me an iterator where the removed value starts, and I just erase them from the thing. So the cool thing is, this reads like normal code. I fetch my position, I update it by computing the speed, I update my speed, I compute how many times I bounce, and I select. This is understandable. Even if you don't really know what's going on and why is it if else instead of if else, it looks like a code you can read again like 3 weeks from now, or sort of. And now we use algorithms. There is no loop there. We only use algorithms. And so the question is, how does it look if I look at the generated code? Okay, so this is AVX2. Let's have a look at run simulation. Let's find the big, yeah, this is the big things. Okay, 16, yeah. Okay, let's unzoom a bit so we can have it. Oh, come on. Yeah. So we got this multiplication add stuff. We have the if else there with the comparisons, and then the subtraction, a bunch more move, again the enrolling of the function, and so on and so forth, and then we jump. And we have 32 bytes per register. We enroll by a factor of 2, so we jump 64 bytes each time. And in the end, we have the tail handling, okay, and we're done. I can actually ask to have that compiled for AVX512 directly like this. I don't touch the code again, and now I can use this downtime to. Oh no, I can't even. Okay, I was about to say, yeah, it's a bit slow to compile, but yeah, it gets better. And if I look at this, I can see that nothing changed. Nothing changed. It's still AVX2 there. Why? Because AVX512 has a bunch of limitations, let's say it this way. So when you activate 512, your core slows down because if not, it will overheat. And so in the end, you may see no actual benefits on your given operations. And so to prevent these bad feelings, if algo never trigger AVX512 by themselves, you have an option to do that. Okay, we are going to have a look at that. So this is normal. So if we try to look at this notion of why is my, where is it? Frequency scaling. We have this allow frequency scaling options that I can put on my algorithms. Okay. So where are you? Is it? So I can say, okay, I want to enroll by a factor of 2, but I will also allow frequency scaling. So this will trigger the use of actual AVX512 operation. So why isn't it done by default? Because this is a performance sensitive changes. So we want people to be able to do it easily by just having this high level change, but we don't want people to suffer the consequence of a byte choice. Okay. And now if we look at the loop, we use this ZMM 64 bytes registers twice, so we skip by 128 bytes per loop nest. Okay. So code is slightly different because, I mean, the way some operations are done in AVX512 is different, but everything changed accordingly to whatever we wanted to do. And last time I checked, we got a nice, almost linear speed up. We got like 3 times 7 speed up with 4 floats or whatever, 7 something on AVX2. So it just scaled correctly as soon as you do. So why don't we force those options on the algorithm? Because sometimes it's okay, sometimes it's not. So we just let people have the choice. For example, the unrolling is not automatic in the sense that sometimes you don't want to do it, because if you have a large function in your algorithm, unrolling do nothing, but you have a very small one you want to unroll a lot, okay? So you may want to experiment with those options. I'm not going into the detail of this one, but this is something we didn't vote actually. We helped the people, but we didn't vote. This coming from an actual database system code base by Amazon. collect indexes, try to find the vector of indexes where a given value are actually fulfilling a given predicate. So you want to apply a predicate on your values, but you don't want the result. You want the index of the values that pass the predicate. So it's a bit more complicated, okay? And so, yeah, that's basically it. Okay, so what we do is we are going to write an actual algorithm by hand in which we are going to load the data, pass over the predicates, and use some non-trivial function to do the biddings. Okay. And I want to enforce the fact that we help the people writing this, mostly on the syntax, and we implemented an option that was missing. But this is something someone using Eve from the doc was able to write after a bunch of time. Okay. So we end up with this rather non-trivial optimized code. I mean, fetching all the index of something that verify a predicate and only having this, it doesn't sound something you can vectorize because you have this, again, size mismatch you have to handle. But it's doable. Okay. One important thing in this is the zip algorithm. Oh, sorry, the zip view even, which is used there, that let us take multiple ranges, okay, and zip them together. So whenever you load them in a wide, you end up with a wide of tuple, okay, in which you can get every part inside the function like we do there. So we zip the data with an index register, and so when we do this, we get the value and the corresponding index, and we can decide what to do with it. Okay. And again, we see that we have another bunch of options. This is a big function. Compress copy is very large, so we want to be sure that we don't enroll, and we want to be sure that there is no alignment taken into account because it will be slower than just loading directly. And so we can just, mismatch stuff like this. Then again, we have the link to the assembly of that, and the code generated. The code generated is rather compact and efficient. The blog post about that basically reported 8 times speed up on their use cases, which is not bad. Okay, so let's conclude about all of this, so we can proceed to questions or remarks. So as we saw, simple programming is not easy, especially if you do it by hand. Okay. So what we wanted to do with Eve is to simplify this exploration of how could I vectorize my code or not. Okay. So Eve is now in a shape of what I like to call, it's production ready. People use it in non-trivial cases. We take a great care to not break everything. We try to minimize the number of changes in the API, but it's still in flux. As long as we are not sure that we can do something in the absolute best way. But we do tag releases, so you can pinpoint whatever version you fancy at some point. It's probably not bug free. We try to squash a lot of them, but we still have like 80 something issues we need to tackle on. So if you test it and something doesn't work, feel free to contact us, drop an issue, drop a discussion, and we are going to try to figure it out. Okay. We are also open to get more support for more functions or more architectures. Okay, especially if you have a use case for a funny function or you have a funky architectures you want to support, and it doesn't fit into what we do, we can help you getting started. We are open to integrate that. What we recommend to do is try to find the most critical components you want to speed up. Try to focus on that, make a better function on that as a standalone component, and then start to integrate it into your code base. And if anything arises, don't feel free to contact us, Dennis or myself. We have a Slack, we have a Discord channel. We try to be very responsive on the GitHub. So we are pretty much happy to get any information from any of you. So thanks for your attention, and well, if you have any question, any clarification, I will be happy to answer them and give you whatever details you need. Thanks again.
Okay, thank you, Joël. So I will check, but it seems that there is no question, but I have plenty of them. So of course,
I know.
you know, maybe everyone is aware of that. Oh yeah, first question, really important. You mentioned that a bit, but it's always good to have it well explained because C++20 is a quite recent language. So, but can you just tell us, since the amount of year of development of Eve? Yeah, I know it's a lot, but it's important to talk about that.
Let's be frank, okay? Current Eve is actually the third rewrite of this. Okay, I have this habit sometimes to find that the code I do is not that good, and I want to change it, and changing it basically means, you know, burning everything and reconstructing afterwards. So the first version was written back during my PhD, so 2000. How much is it? 2003 to 2005, some sort of, yes.
Yeah, so 20 years ago.
20 years ago. Don't say that. I mean, I'm trying to.
Yeah, but it's important. 20 years of development,
20
it's a
years
lot.
of development. So the first version was basically Altivec and SSC 2 to 4, something like that. It was a 2 people effort, me and Jean Thierry. It was already there. It lived this way for a while, and then we tried to extract it. At some point, we wanted to have that into Boost and then into the standard. It becomes something called Boost SIMD. It grew a bit more, but then, I mean, life happened, and I went to do some other things, and I found out the way we are doing the thing was not absolutely the best. And it was around 2012, so C++11 was there, so we migrated to there. And later in 2017, other life events, I ended up deciding we need to do that, but using C++17 because it will be probably better, because all the new template stuff, if const expert and whatnot, was actually useful. And 2 weeks in, I will be very frank with you, 2018, 2 weeks in the rewrite, GCC drops C++20 support. And I'm like, oh, maybe I should have a look, because maybe, you know, later there will be interesting things. So I start experimenting, and 1 week after that, I'm like, okay, in fact, we are going to jump into C++20 directly because it's far better. So the third version, which is what we have now, it's 2018 since now. So this version is like 7 years old. Okay, with a big boost in productivity when Dennis came along in 2020 something, just before COVID, I guess. Yes, 2019. Okay, so 2 years after. He helped a lot with the algorithmic side of it, and then we kept getting the momentum rolling. So yeah, the current version is 7-8 years old, and the YOL project is almost 20 years old now. So it's old enough to vote, and almost old enough to drink in the US. So
yeah, so that's a lot of work. So you don't want to write that yourself. Use
you don't.
Yeah, you really don't want.
I mean, even myself, sometimes I don't want to do it, but I have to. But yeah, I mean, it's a lot of aggregated knowledge from what we found out, from other people found out also. We also owe a lot to a bunch of people from Intel and from from a lot of people from Stack Overflow, Peter Cordes, Baliviak, some of the people that help us, you know, brainstorm some solution. For example, the compressed copy, the way we handle some things, the algorithm, we got external help for that. So it's a collaborative effort. So and it's probably one of the last places where you can find some actual verified optimization technique for some of the architecture we support. The one reason why I don't drop, because I could actually, why I don't drop the PowerPC support is because it's probably the last place where you can find aggregated information on how to actually make Altivec works properly. So all in all, it actually has some kind of historical value too. So there is that.
Oh yeah, maybe it's a question maybe for Kiwaku, but
yeah, I didn't speak about it, but
yeah, you didn't speak about Kiwaku, but
yeah, I'm trying to keep that for July, but
okay, I keep my question for June.
But Kiwaku is basically the next step into this. We have a Joël, taking over the work plan. This is one of the bricks of it. Kiwaku is the next one, which is it's a C++20 library for efficient data storage, okay, and processing. So it's basically the storage complement to Eve, and the plan is to combine all of that to get back to having a proper numerical computation, not library but ecosystem based on all of that. Not a library but ecosystem, because we went the one size fits all library path once, and it's a disaster. So we have this stance where we just try to slice, every piece of it into a different library that is, obviously compatible with all the others, so people can choose what level of things they want to do. So they can have the old things, they can have only the storage, they can only have the vectorization, and so on and so forth. So yeah, we're probably going to speak about Kiwaku in July or June, actually. But yeah, this is something that's a surprise for later this year.
Okay, so I'll keep my question for the school.
No problem.
Oh yeah, you mentioned also, as Adrien said, before using multi-cores, use one core well, and then you can use several cores.
Yeah.
Oh yeah, I have a question about your strlen function.
Mm-hmm.
What happened if you don't have a number of character which is not a multiple of the number of the vector register?
We don't care. we don't care. We don't care because of two things. We don't care about that because of that. I'm going to explain this. And we don't care because whenever you allocate data, data are actually allocated in pages. So you don't care if you spill out a bunch of bytes at the end of your array. We found about that, and this is something which is actually guaranteed by the system design. And so what we do is, I didn't speak about it, but when you pass a function to an Eve algorithm, the function you pass is supposed to work on wide. You don't need to have a function that work on wide and scalar. We only need the version working on wide. Why? Because whenever we hit a tail or a prologue, depending on how we do it, we are going to load a full wide anyway, because we can. Okay, and the extra data are handled by this ignore stuff. So we ignore the last part of the tail that contain garbage, right? And so we can compute everything as a vector. So we don't actually care, because in the end, if you don't have a matching size, you ignore the thing, okay? And you won't process this garbage, okay? And so you don't care, actually. Because if you think about it, strlen doesn't sound something you can vectorize, because you don't know how many things you are going to load, and you don't know if you have a fixed size number of vectors. But in fact, you don't care. You don't care because you can apply these tricks that you can read a bit more at the end of your vectors or at the beginning. So that's why we do this previous align load, okay? To start from something which is aligned and then keep it up, everything like this. So you don't actually care. I mean, in Eve, you don't care because you can ignore the garbage and whatever. And actually, having garbage in vector is something we actually use in the algorithm design to be sure that we can optimize a lot of things. And we have these unsafe things. What unsafe does, it basically do nothing. It just do the load, but it peppered the load implementation with whatever attributes you need, so that if you pass this code into what's the name, a sanitizer or Valgrind or whatever, it won't bitch about the fact that you are reading past your data and whatnot. Okay, it's just a way to shush the sanitizer, because we know what we are doing. Okay, and one thing to understand is when you're writing code like this, you have to make the compiler and the tool understand that, yeah, if I do that, I have a reason. Okay, so a bunch of the tricks we do in the implementation is to actually, make the compiler behave, so we can be sure we get the exact, behavior we intend to.
Okay.
Oh, there is question now, apparently.
Yeah, there is question now. So from Julia, I am new in vectorization field.
Yeah.
I attend different webinar on the topic. What are the benefits using EVIT compared to other vectorization library like Cocos or maybe SCMDE or XSCMD or just
Yeah,
STD Sander like?
I can probably do a quick sweep on that. For me, the only actual things that look a lot like what we do is either XCMD or the standard CMD proposal. XCMD is actually good for the one reason I know that because most of their implementation of some function came from our Boost CMD implementation from 10 years ago. And I'm very glad they are still in use somewhere. They have a different approach to how they define. I'm not a fan, but makes sense in their, framework. Okay. So XCMD is good. It's C++11 only, so that's probably one advantage if you are stuck with all compilers. But in the end, we probably get very similar performances because there is no that much way to compute what we compute. We have a bunch more functions than them, but that's basically just a difference in feature sets. Cocos, what do you mean by vectorization in Cocos? Because Cocos, you got this array-like operation, but I don't think Cocos do any specific vectorization, does it, Pierre?
Normally it's supposed to.
I'm not a big. It probably doesn't hinder autovectorization, but do they have an actual vectorization layer? I don't remember. I don't know. Maybe they have.
Normally, yes.
They have, but how it is done? Manually, like us, probably. Yeah. Well, I will have to check that.
We have to ask
I don't know.
David for that.
I will pester David or have a look at Cocos. And the standard CMD one, well, it's a doozy. In the end, the standard version is basically VC. After I don't know how many pass of design by committee passes, okay, for the best and the worst. Again, VC has very decent performances. Again, because when you are at this level, you either do the thing correctly or you don't. So there is no in between. The standard CMD is a bit more limited than what we do. They do choices that we don't agree with. The fact that if you use a data part type, it's basically the lowest SIMD instruction set you can have on a given machine, while we aim to get the best one. And we are not very fun about the API and the naming, but that's probably just a matter of byte shading. But I don't see. We are going to give a talk at CPP now next week, and we do an extensive comparison with the standard. But basically, in terms of performances, whatever we have and they have is basically the same, except we found that our API is better. And about STD unsec, when it works as good as your autovectorizer. And when it doesn't work, you don't know it because you just happen to end up with a scalar code. Unsec is getting there, but it's basically just a way to tell the autovectorizer to do its jobs a bit better. So it's as good as whatever your autovectorizer is. Okay. There is no, sorry if I will make a comparison to something else, but no disrespect is meant. Autovectorization in compilers, it's a bit like what was the name for that in English? It's a bit like controlled nuclear fusion. In 10 years, we are going to have it. Okay. And I started doing vectorization work in the 2000s. Someone at my PhD defense told me that in 10 years, my work would be useless. It's not. Then when I did my HDR, someone told me that maybe now, in a bunch of years, we won't need that anymore. It was in 2012. Spoiler. And there is a wax and wane interest into the manual CMD vectorization things, because people think the compiler do everything until they basically check it does not. So they try to do something. So there is a bunch of projects that basically work exactly what we do, that come and go every 5 or 6 years. Okay, it is still an open problem because there is a lot of things that autovectorizer can do, because contrary to you, they cannot take the option to say, oh, I don't give a crap about precision there, so I will just do these very crude things. Compiler must preserve the semantics of the program, okay? And they cannot do a bunch of those things, okay? So autovectorization is basically what unsec is doing. So it's basically limited to whatever you have. For example, you can try to put an unsec on std sort. You won't get a vectorized sort. I mean, it's not working like that. So what we think we are, and we have some benchmark to prove it in different of our presentation and papers. Whenever we do some high-level algorithms things, because that's the interesting part, we have like 95% of the expected speed up on those things, depending on the architectures. For all the smaller benchmarks, like the micro benchmark on a per function basis, except for stupidly complex functions that cannot be vectorized properly, we got also a large fraction of the speed up. And for some of them, I would say that I would just be trolling a bit there. But basically, we have infinite speed up because there is no other vectorization implementation of those functions. So they go as fast as they go, but they are vectorized. I'm speaking about our special function vectorization, about all the combinatorial computation we do. There is no support for that anywhere. So that's also a plus that I think we have. And to go into this, maybe answering Sergey in the meantime, yeah, Rust synthesization. I know two things about that. There is a standard SynD support in Rust, if I'm not mistaken, which is basically, I guess, a Rust version of whatever stdcmd tries to do. Last time I checked, it was doing a decent work, but basically because it's compiler based. So I hope they do a good work. There is also, what's the name for that? There is also a, is it Fair? No, Fair is the linear algebra. There is another effort of a natural library for vectorization. Pulp, yes, thank you, Adrien. Which is a bit better. I very much like the design, and I know Sarah personally, and she's a great developer. There is a bunch of things that we could have, which is, for example, the fact that you can compile your Rust pulp base code for multiple architecture at once, and you will pick up the correct one at runtime, something we cannot do with Eve without doing something manually on top of that. But then again, I mean, in the end, we are forcing the compiler to spit out exact intrinsics. So, I mean, in terms of, performances, we are probably at the same level. We probably need to make a Rust comparison at some point. But, I mean, looking at the generated assembly language give me whatever information I need. And again, for small function, you don't have that much way to compute whatever. And so the only interesting part is to see how it behaves in terms of algorithm and stuff like that. But I don't expect to have a lot of differences anyway.
Okay. Questions from Vincent? Some architectures have non-consecutive load stores with a base address on vector of offset. What is the performance cost on these non-consecutive load stores? For small computations, is the cost too high for vectorization still worth it?
Yeah, gathers were introduced in AVX2 and SVE. Scatters in AVX 512. So gather and scatters, instead of loading from an address or storing to an address, you have a base address and you have a vector of index. Okay, so you can say from this array I want to get index 3, 7, 1, 10. Okay, so you spread out and you load into a single thing. So there is no magic there. The culprit is how many cache lines are you touching with this gather or this scatter. If everything you load is in the same cache line, it will be slightly slower, but not by much. But as soon as you do something, so the worst thing being, for example, if you want to use a gather to read the data in a transposed way, so you will go and touch number of lanes, different cache lines, then the performance will be very bad because you are going to pay for the cache issues and whatever. But if you are in the same cache lines, how to say that, the overhead is okay-ish. Okay, it's slower than a regular load. If you start spreading out on different pages, then it's a mess. So sometimes you have this issue where your data is big enough to fill out 2 pages, and your gather is actually crossing the page boundaries. Okay, and this one gather will be terrible if you scatter into the same place twice in the same scatter. Okay, I don't know how the system works, but I guess you have to be careful about that. So usually what you want to do is, if you do, let's say you do gather, okay, because scatter is another word, okay. If you do gather, that means because you have a complex loading pattern, okay, in your data set. The question is, can I actually do it with a regular load and a shuffle, which is most of the time faster, because you turn your irregular memory access into a regular memory access and some computation. And for the people around there that are aware about, the computation memory cost ratio is actually beneficial to you. Now the shuffle may be non-trivial, and so maybe you have to massage your algorithm so you get to a trivial shuffle. But it's usually, even in the non-trivial shuffle cases, it's usually better. And what compiler do, and that's what we try to do, is sometimes your shuffle makes no sense. For a shuffle to make no sense, it means that you need more intermediate shuffle to get your result than you have values in your vector. So if you have 4 elements in your register and you need more than 4 shuffle to place the data, you are not going to win anything. And in this case, the compiler just do a gather, and we are going to try to do the same. Because instead of doing that, you do a scatter, you pay the complex, memory access cost once, and you're done. But if you are, if you wanted to do something like taking one element out of 2 or out of 3, something like that, it would be probably good because you still have a lot of data in your cache line, right? But if you try to say, okay, my gather is 1, 10, 100, 1,000, then you will get bad performances. That's basically what happened. So, which means that the general A of B of I loop is still bad if your B are very spread out. But if you are sort of spread out but not that much, it's okay-ish. But we don't recommend starting with that unless the equivalent shuffle is very complicated. But you want to do shuffle most of the time. Our cache line, yeah. Normally, on regular processors, cache lines are 64 bytes. So that means that you can fit, how much is that? You can fit 4 semi-registers of SSE and one single AVX512 register on the cache line. So yeah, 64 bytes. So as long as you have this window of 64 bytes in your gather, it's probably okay. But as soon as you go over that, you are going to. It's a bit like I'm making a long shot there. It's a bit like this issue with in GPU when you do this loading from the main memory and you want your access to be coalescent, you have to be careful not to drift too much apart or to mix the things in a too complex way. That's a bit the same. You can fan a bit, you can gather, you can broadcast a bit by PCs and whatnot, but as soon as you go everywhere, you will get awful performances. You're welcome, Vincent.
Okay. So yeah, you spoke about a bit about unrolling. So
yep.
Apparently for now in EV you have to put the value, the number of time you want to unroll.
Actually, if you don't put anything, we unroll by a factor of 4 because that's the usual factor that work well on a regular machine with a regular function parameters. But as soon as your function is very big, unrolling is not helpful, so you want to reduce it or even removing it. And for some operation, even if the function is small, the way your data are set up may require you to load less, to unroll less. So basically, we have this default thing. Let me see if it's, where is it? Not this one. A simple one actually. Oh, come on, where are you? Yeah, unroll 2. If I remove that, okay, if I unroll with everything, yeah, okay. Yeah, where is the loop? Yeah, it's probably 256. So we have like 1, 2, 3, 4. We enroll by 4 by default. But maybe you will find out it's not optimal, so you want to try a bit less, you want to try a bit more. So we have this option, but basically we just enroll by 4 because most of the time it's enough. In this case, it's not good because we do a lot of computation, some amount of computation. And if you run the benchmark, code is actually into the example, into the Eve repository. Enrolling by 2 is most of the time enough. And so, as I said, we can't know in advance what you are going to put into the algorithm, what kind of data set you have. So we have, finger in the wind approximation that works well for every basic cases you may have. Okay, and we have this option to say, okay, I tested it, it's not good. What kind of lever do I have to change that? So you can enroll less, up to nothing, basically, if you wanted to, which is probably a good idea, a better
You
idea
can
in
put
this
0.
case. No, you
Say,
can't.
I don't want to do this computation.
Yeah, we should do that. I mean, okay. Oh well, what happens if we do it? I think I don't know what happens. It would be funny if we just do that. And it's so we can have a nope thing. So, but yeah, it doesn't work. It's probably trying to divide something by 0 and it's not happy with that. Yeah.
It's not a good idea. Okay.
But maybe we should have a concept check on that. But yeah. So we have all those bunch of options. So that's the idea. So people can experiment. They have the main skeleton right. It's an algorithm applied on data set with a function parameter, and all the low-level things are tweakable from the outside. Okay, and so the non-enrolled version is basically exactly what you want. So yeah, and for example, for remove if has a no enroll by default because it doesn't make any sense. So some algorithm has different default, but we try to fit the default to whatever the algorithm is doing.
Yeah, because that's the main problem. Once you want to enroll, you increase the number of registers you want to use, and maybe you don't have enough. That's a problem. If you want to do it well, you need to have the number of registers you can use. It depends on the architecture, and you have to gather this information. And
we have this information in a contextual variable somewhere that you can use in the API, but we put it there because we were thinking it would be useful to have people design complex computation to put into the enroller or whatever. In the end, 4 works like 80% of the time, and the 20 other percent it's 2. So we keep the values there because they are part of the API, but I never saw any people using them to do this. At some point, we wanted to use them automatically, but I mean, in the end, the result was 4, so we just put 4, and we live with that. Yeah, where I think it's in the where is it? That's a good question. Where is it? Arch, probably. Platform sounds good. No, it's probably not there, but. Oh no, so that's the NaN and stuff, so it's not there. Okay, I was thinking it was there, but somewhere we have something like that. We also have a runtime detection system. I didn't speak about it, so you can check at runtime that you have something, and then you can call the proper variant. So we have this this CPU ID based crap that you need to do, and we have a tutorial about how to handle that. So yeah, it implies having something that loads, like we get some DL open things, and we have a special CMake support for that. So it's a bit more complex than on other system where you can just compile with multiple things. We found out that most of the systems that do that, especially stuff like Highway, do it slightly wrong, and I think they end up with silent ODR violation. We are also not sure how it will work with modules. That's something we want to include at some point. So currently what we ask people to do is this. So you have multiple binaries that you load dynamically. And you can pick and choose whatever variant of your code you can get. There is work being done to simplify that, but it implies doing a lot of changes at once in the library. Because one solution could be to wrap every Eve function into an inline namespace whose name depends on the current architectures, and so you can include them multiple times with multiple options, and every symbol will be different depending on where you are in your binary, and then you can call them. But yeah, I mean, not sure it works with modules, not sure it works actually well. So for now, we support this, and it works, okay? And it works like all the time.
Oh yeah, once you combine with std-find
Yep.
your performances, why don't you compare with std-find-if with
Because
your
std-find,
EV?
okay, because std-find-if is worse than std-find.
Okay.
Because the fact that it has, where is it? This is actually a hard test for us because we are looking for a 0 in the data. Okay, and what we do is we call if find if with the predicate that say is my value equal to 0. So we have to go through a predicate, generate the predicate, do the computation, do the masking, do all the things. Where we use a steady find of 0, because a steady find you actually use std memshare, which is very fast and optimized and vectorized all to the wazoo, okay? And so we compare to this. But a steady find sometimes doesn't get there because as soon as you have non-trivial types or something, it doesn't go there. So std find is actually faster than we are, should be faster than what you got, okay? So that's the ultimate test we should have. And we are faster than std-find in all scenarios because we do a bunch of things they don't. Namely unrolling, namely the tail handling is different and stuff like that. If you compare to std-find-if, you have a twice as much, you have a twice, 2 times more speed up on that. Some implementation of std-find is better than others. Recently, which one is the libc one? Get improved. And today, if I draw these things, everything is basically twice faster for std-find. So we are matching on integers, and we are only like 3 or 4 times faster on the other things. The other thing is that most of the time, those functions are vectorized for the lowest denominator of the architectures. So they are probably vectorized for SSE, something. And we do get better because we target all the other things. We have updated graph for that that we are going to present a bit later. But we still, I mean, we are on par with whatever the standard is doing when it finds out that it can use a very fast function at like 10%, 5% of it. And whenever the compiler gives up, we still deliver. So one thing we were seeing for a while was the tagline should be, I mean, if it compiles, it's vectorized. Okay, so that's somehow guaranteed that we do this. So yeah, we compare to find because it's actually harder to compare to find. Find if is a mess because you have an if in a for loop and most of the autovectorizers just give up. So yeah, well.
Yeah, it's normal. Okay. Oh yeah, for your little bouncing ball example, you don't want to be ashamed of that. You want to tell that you use the Euler method.
Okay. I will do that.
So that's more scientific.
Yeah.
Coloring
the balls,
without joking,
like
if I create a ball and I say, okay, I want to do some physics with it, and I use a vector for the position, for example, can you split it once you want to convert it into a structure of array, or do I have to give some int to have?
SOA vector as a constructor that take multiples array.
Okay.
And zip them. So you can just construct this SOA vector. Oh, sorry. The SOA vector that we don't see there. Where is it? Where are you? Yeah, this SOA vector, you can construct it in different ways. And one way is to basically gather different vectors and put them inside.
Okay.
And if you don't want to do this, if you don't want to use SOA vector at all, because you don't want to copy the data, so you have your 3 vectors or your, 4 vectors defining your balls. You have the vector for the position, the vector for the speed and whatnot. What you can use instead of this is you can pass a zip view of all your vectors and it will just behave the same.
Okay.
So you can, no way. You have to zip view and you have to pass an option to the algorithm to say that, yes, I'm giving you a tuple of things, but this tuple of things is actually a ball. Basically, we have an option to say this tuple is actually a type we know about, and we do all the conversion for you. We found out that having this tuple supports directly into the library is very useful, because you can just write complex code directly first with a tuple, and then you can put your data structure, or you can deconstruct it, pass it to the vector things, and it just works actually. And that's one difference we have with the standard proposal, because we have a wide of tuples whenever we do zip and stuff like that, while the standard have tuple of wide, which is a bit stupid, because that means that your generic code is not generic anymore, because you have to know, is it a regular type, or is it a tuple of something that I need to, deconstruct? And we found out by experience that having this wide of tuple things just work better. And obviously, behind the scene, it's a tuple of y, because that's the way we want to store them. But the API is based on the fact that if you have a t, you can vectorize it as a wide of t, and it always works. Okay, and whatever operation you can do on t, you can do on the wide of t. That's the motto we try to have.
Okay. So, I have one question about your backend.
Yes.
So you have all this construct if in your backend.
Yep.
And I wonder is it possible to say, okay, I want to call CUDA PTX this time, and to generate some GPU code? Is it something which could be possible, or for AMD, for NVIDIA, for Intel?
At some point, I mean, this question pop-ups like every now and then.
Okay.
The answer 10 years ago would have been, yeah, we can probably do this, because what we can do is we can have a wide to mimic a warp, and we can do something with that. Right? We actually tried to do this at some point. It was working in the sense that it compiled and get something. But the programming model is completely different, as Adrian says. I mean, in this case, we are writing at the level of the register, where what you want to do with CUDA or HYPE or whatever is you want to write at the scalar level of the kernel. So maybe what we could have is that the algorithm could do that, but it's not very useful, because you can use, I don't know, you can use Rust to do this, or whatever the
I was thinking about
OpenCL equivalent. Yeah, but we are not at this level. We are. I mean, if I go with the CUDA metaphor, CUDA has Rust based on cub that works with generating the low-level code.
Yeah.
Okay. We need to have our trust equivalent, but basically Eve is at the cub level. Okay, it's the things that let you write the other complex stuff. Okay, and there is one reason I don't want to do. Yeah. The other thing I will actually say it somewhere. Yeah, it's a job for another tool. Again, it's explicit SIMD is explicit SIMD. It works well with a bunch of things. Implicit SIMD, like on, SIMT actually is very different. And I made this vow at some point to stop trying to, fit everything into a single box, because it's complicated to maintain. It's complicated for people. So for a long time, I was about to say, oh, maybe later we are going to, make something about GPU work. But then Cycle came along, so we just use Cycle now whenever we need that. But it's not the job for Eve. I mean, it could have been. It could be even now. Maybe if you wanted to be at the level of, like the what's the name for that? Those vector types you have inside the GPU, the float 4 and whatnot. But you are not going to win a bunch by renaming float 4 into something else. It's not gonna win you anything. Okay, maybe could have an interest if you do shaders, but I'm not even sure it does. And it's not something we are willing to entertain inside of Eve, because for us it's out of scope. Okay, and I'm very adamant about this scope, strict scoping of whatever the library does, because if not, it turns into an unmaintainable mess. We had one library like that, and I stopped maintaining it when I found out that every time I wanted to add a full support for new architectures, I required an increasing number of PhD students to do it. Okay, which is not sustainable. Okay, so we slide that. Okay, so if if something like cycle didn't exist, maybe we would have had something. But now we just use cycle for that. The only thing we need to find out is how can I use cycle in multi-threaded mode and still put Eve inside the cycle kernel. That's another question. And maybe there is a place to do some funny things. But yeah, we are not going to touch the GPU and as I said, the same way we are not going to support the dynamic runtime sized SVE because it doesn't make any sense in terms of what the programming model is. And the compiler doesn't support it anyway properly, so we just have to live with that. So SVE support with fixed size. All dynamic size GPU-like systems are not supported and probably won't ever at this level of ABI.
Okay, I have a last question because you didn't mention it during your presentation. Can you show us your sine and cosine optimization once you want to select a quarter of the? It's really important to have that in mind.
Okay, let's have a look at that. Let's say we have something like this. Let's generate some values. Okay, something like that. I don't know. So I use this lambda to fill up the void. So we got the whatever is inside. So yeah, we have this sine, cosine, whatever sine is. So we can take a wide of float, let's say. And so we have a, let's say, I don't know, let's take cosine, for example. Okay, what about all the letters in the correct order? Thank you. Yeah, so I'm trying to call cos. Okay, I'm not calling it there. I just want to look at the assembly. Cos is a complex function. Okay? There's a lot of way to compute it properly. What we do is that we use some obscure decomposition things. Okay, and cos, when you pass nothing, it generates this. Where is it? Where is f? So that's a constant we use. We have a bunch of them, as you can see. And then you have this very, 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 very long function. But I assure you, you don't go over all of that. There is different function inside. And what cos does, it looks at your values and it tries to know if are they all into some boundaries that let us simplify the computation. Because if your angle is between minus p over 4, p over 4, you can compute it with a very small polynomials. P over 2 is another one, half of the circle is another one, and so on and so forth. But the standard cos, you can compute cos of 10,003, so we have to do it. So cos usually start by having a reduction of the value to some amount of that fit into the unitary circle, right? Because it's basically modulo 2 over pi, not funny. And then you do the computation. Your inputs are, I don't know, within this minus plus p over 4, okay? It's a very small one. You can actually say, oh, you know, I know that. So let's work in the quarter circle as my input, okay? So now what does it do? If you are actually there, it does the computation with a better algorithm. We are going to have a look at it. And if not, you get none as a result. If you get outside, you get none. And the function is basically this. Okay, so let's do AVX2 because the code is a bit better because this is SSE and it does a lot of cruft. It's probably, it's basically a bunch of broadcast and add mul, so which means that I can probably trigger FMA if I want. And bingo, I got FMA code. Okay, FMA. It's 1, 2, 3. It's 4 FMA and a comparison at the end. Okay, so it's very smaller. Okay, and it's like 4 to 6 times faster than the other one, which is already 2 to 3 times faster than whatever acidic cost is doing. Okay, but sometimes you need more than that. So maybe your data is in half of the circle. Okay, and then the polynomials grew a bit. Okay, broadcast, and we do a bunch of blend, and we get a more complicated, polynomials, but it's less than the whole thing. Okay, and if you know that you have something which is between 0 and 2 pi, but never above that, you can ask for the full circle. It's a longer one again, but it's not the crazy 1,000 instruction ones. Okay, It's a bit long, but it's manageable, right? Okay, it's like 70 instructions, okay, and a bunch of broadcasts, okay. So we have these controls over this. We have the regular one, like the raw one, the pedantic one that works almost everywhere. And then some function family have their own special tags. So this is the one for trigonometrics, okay. And for example, you have one for all these, compress, remove things. Because if you know, for example, that you want to remove a lot of value from your data, that means that your predicate is dense. You can say it, and if you know that you will remove very few, you can say that your predicate is sparse, and then you have two different algorithms. And so if you don't put anything, what happens is that we have a bunch of tests that say, are all value small enough to call the fast one, then we do it, or are they all into the larger one, or the very large, or is it whatever? And when it is whatever, we do the full quarter reduction and then the full-blown algorithm. Okay. And in the end, we found out that this thing is actually fast enough to get a proper decent speed up compared to STD cost. And the quarter circle, for example, on AVX2, it takes basically 35, 40 cycles in float to compute one cost with STD cost. Okay, so 40, okay. And the quarter circle cost is 3. But in 3 cycles, I actually computed 8 cosinus. This kind of speed up we are speaking about. Okay. So those reduction on the data set, those reflection about what kind of precision do we need is actually important. And that's the same thing for the square root, actually. Yeah, on x86, probably not very a big difference, but basically, if we do that, so we end up with, we call that because it's basically what we can do the best, okay? But if we were, do I have another? No, I don't have. Okay, I could actually run that on PowerPC, and on PowerPC, you have to do multiple. Oh, let's do it, actually. Can I? No, I can't. Maybe I can. No, I don't have it. Okay, if we are doing it on PowerPC, square root is a bunch of 4 to 6 instructions. And when we ask for the raw one, you just got the one instruction in 26. That go like 3 times faster than the rest, except if you are okay with your square root of 4 to be 1.999997, okay, something like that. So we have all those, those levels. So and the trigonometrics one are we are probably the only one having that. And the algorithm we use for sinus and cosinus is actually funny because it actually computes both at the same time, and we just mask whatever we need. And so which means that basically our sin cos function is just basically 1.5 cycle slower than sinus or cosinus, instead of costing the time for doing both, because we can share so many elements from the computation of the extrapolation. Okay. We spoke about Raberu, but something I want to speak about also is, where are you? We have another companion project which is called Kyozu. It's not done yet, as you can see. But it's basically complex computation, so complex quaternion, octonion, and whatever else. It's based on the application of the Cayley-Dixon algebra formulas on real numbers. And so basically, it's a recursive implementation of complex. And we basically support every function we have in Eve. They are all vectorizable through Eve, except they work on complex types, like like the one that I don't have there. So we have stuff like this. So where are you, complex? Yeah, so we have these complex types. Okay, if you ever do a wide of Kyozu complex, you get your complex vectorized by the library. Okay, and so this is one of the companion projects we have for Eve. We have another one which is not public yet, which do the same tricks but for computing automatic differentiation using the what's the name for that? Dual numbers. Okay, and the all dual numbers computation are vectorized with Eve in the backend also. It was in Eve for a while, but as you can imagine, that basically doubles the number of tests we had to run, because we have to test for every type in scalar and then every type in complex for functions which are far more complex. Okay, so we finally extracted them into their own library that depends on Eve. Okay. So it's a bit rough yet. It's getting finalized at the moment, but we plan to have a bunch of those, adjacent compatible library for those very specific numerical computation systems.
Okay, thank you, Joël, for the great presentation. So now it's time to stop. So
Thanks
thank you
again for having me, and see you in July.
Yeah, see you in July for a full lecture about everything that we just mentioned right now. Exceptionally, so next week and the week after, we will not have Grayscale Thursdays because they are day out in France. So we will meet next time, the 15th of May, for Python webinar lecture about Python CPUification and GPUification with NumPy, with JAX, with a lot of library like this. So don't miss this presentation. See you the next time, the 15th of May. And have a good day. Bye.
Bye.